Hello everyone, and welcome to the Smart Curve Digital Learning lesson on the solar system. Now, hopefully you remember in our last lesson, we took a look at the sun, the earth, and the moon, and we learned about the behavior of some of these bodies, specifically their revolution and rotation. We also looked at the force of gravity that shapes these behaviors, that affects the way the earth revolves around the sun and the moon revolves around the earth. Today, we're going to expand the discussion a little bit, and we're going to take a look at the entire solar system. Now, by this point, we know that the sun is a star and the earth is a planet that revolves around that star. However, we also know that the earth is only one of 8 planets that revolve around that sun. And that just like the earth, many of these planets also have moons and atmospheres. So we're going to take a look at all of these different planets and some of the other bodies that we've got revolving around the sun. So here on slide 5, we're going to take an overview of the planets. In the first bullet point there, the terrestrial planets. Now, terrestrial, that word comes from the Latin terre, which means earth or land. Go ahead and circle that. Yeah, terre, meaning earth or land. So these are the planets that are rocky and relatively small. That would be Mercury, Venus, Earth, and Mars. These, of course, are the 4 closest planets to the sun. The Jovian planets, and that next point, notice that name, Jovian. That comes from the word Jove. Now, Jove is another word for Jupiter. Jupiter was the king of the gods in Roman mythology. And actually, all of the planets in our solar system are named for ancient Roman gods, all the way from Mercury to Neptune. But the planet Jupiter was given its name because Jupiter is the largest planet in our solar system, and so it was named for the king of the gods. And because Jupiter's other name was Jove, we now refer to all of these outer planets as the Jovian planets. And these are huge gas planets. They're much larger, much colder, and they're largely composed of gases, especially hydrogen and helium, but also gases like methane and ammonia. And we will take a closer look at this later in the lesson. Pluto, that last little one, does not fit into either the Jovian or the terrestrial category. So depending on what book you're reading, Pluto might be considered a planet and it might not be considered a planet. There actually is still a lot of debate among scientists about that question. Do we consider Pluto to be a planet? But whether we consider it a planet or not, it doesn't really fit into either category. On slide 6, we can see a picture there of the solar system with the sun there at the center and all of the planets with their elliptical orbits revolving around the sun. A couple of other features here, a couple things to notice. Take a look between Mars and Jupiter. We see that belt of what looks like brown dust. That is the asteroid belt. Asteroids are small rocky objects that never really formed or became part of a planet, and we're going to take a closer look at those later in the lesson. Also, outside of Pluto's orbit, we see something called the Kuiper belt. This is a belt of comets that have a largely circular orbit, almost perfectly circular orbits around the sun. And we're going to take a closer look at these as well. The asteroids there in the asteroid belt and the comets in the Kuiper belt. Another couple of things to notice about this picture. Take a look at Pluto's orbit. Looks quite different from the others. It's almost as if all of the other planets are there in that one flat plane. Remember, we learned about this in our last lesson. It's called the ecliptic. All of the other planets lie on that ecliptic, but Pluto looks as if its orbit is tilted, slanted relative to the ecliptic. So we're going to take a closer look at that as well later in the lesson. Some more things to notice about that picture. Remember that the sun is many, many times larger than any planet in the solar system, even the large planets like Jupiter and Saturn. So we could never see the solar system like it's drawn in this picture, because if we were far enough away that the sun was just a small dot, like half of a centimeter across, then Jupiter and Saturn, Uranus and Neptune, all of the other planets, would be only tiny, tiny dots of light, if we could see them at all. So remember, when you're looking at this picture, it's not drawn to be accurate with respect to size. And then finally, let's look here at the bottom of the picture. Notice down here we have a diagram that shows the relative location of the different planets. Notice if we have the sun over here on the right side, you can see here MVEM. Of course, this stands for Mercury, Venus, Earth, and Mars. You can see how close all of these planets are to the sun when we compare them to planets like Jupiter, Saturn, Uranus, and Neptune. If you look at it, you can see Jupiter, for example, is almost twice as far from the sun as Mars. And Saturn is almost twice as far as Jupiter. Uranus is almost twice as far as Saturn. So as we move out from Mars to Jupiter to Saturn to Uranus, the distance, not quite, but almost doubles with every planet. So the planets are not evenly spaced. Let's move on. On slide 7. Size is the most obvious difference between the terrestrial and Jovian planets. Obviously, the terrestrial planets, Mercury, Venus, Earth, and Mars, are much smaller, whereas the Jovian planets, Jupiter, Saturn, Uranus, and Neptune, are much larger. Density, chemical makeup, and rate of rotation are other ways in which the two groups of planets differ. And we're going to take a closer look at all of these features throughout the lesson. On the next slide, number 8, we have a large chart of planetary data, a lot of information on all of the planets. Here we've got all of the planets going down the left side of the table, and for every planet we've got the distance from the sun. You can see here Mercury is the closest planet to the sun. It's only 58 million kilometers away. Pluto, 5,900 million kilometers away. So that means that Pluto is about 100 times farther from the sun than Mercury. 100 times farther. In addition to distance, this chart also has information on the period of revolution and the period of rotation. Remember, the period of revolution would be answering how long it takes the planet to make one trip around the sun, and that period of rotation asks how long it takes that planet to turn on its axis. So 1 day. Notice for Earth, our period of revolution, 365 and 1/4 days. Our period of rotation, 23 hours, 56 minutes, and 4 seconds. One very interesting thing to notice about this data is with the planet Venus. You can see here the period of revolution is 225 days. So a year on Venus is 225 days. Its period of rotation, 244 days. So a day on Venus is 244 days, where a year on Venus is 225 days. So on the planet of Venus, a day is longer than a year. Very strange. As we move out from the sun, you can notice the period of revolution for some of these planets becomes very long indeed. Mars has a period of revolution of 687 days, so that's very close to 2 Earth years. Notice Jupiter has a period of revolution of 12 Earth years. And notice its velocity is much less, so Jupiter revolves much slower. It revolves about half the speed of Earth, and it takes 12 times as long to do it. Saturn, notice, again, revolves even slower than Jupiter, and because it's got a much longer path, it takes almost 30 years to go around the sun. The next planet is a rather interesting one. Uranus takes 84 years to go around the sun. But another interesting thing about Uranus is its axis of rotation. Remember in our last lesson, we learned that if we have the ecliptic, Earth's axis of rotation is slightly tilted, so that one side of the Earth is always facing the sun, having summer, and one side of the Earth is facing away from the sun, experiencing winter. Now Uranus, on the planet of Uranus, that axis of rotation, like Earth, it's tilted, but it's tilted much, much more, so that Uranus's axis of rotation lies almost on the ecliptic. So it rotates top to bottom and not around. What that means is that one side of Uranus will face the sun for about half of that revolution, or about 42 years, and then it will be away from the sun for about 42 years. So on the planet of Uranus, you have daylight for 42 years, and then darkness for 42 years. All right. Let's move on. The planets, an overview. Here we are on slide 9, the interiors of the planets. The substances that make up the planets are divided into 3 groups: gases, rocks, and ices. We've talked quite a bit in our geology lessons about the different rocks that make up the planet Earth, the different silicates, in addition to the different ores that are down in the core. Then the atmosphere. The Jovian planets have very thick atmospheres of hydrogen, helium, methane, and ammonia. I think it's good to mention here that hydrogen and helium are the main components of those atmospheres. For example, Jupiter has an atmosphere that is about 88% hydrogen and about 11% helium, and only 1% of the atmosphere is everything else: methane, ammonia. There's also some phosphorus and sulfur compounds, and we're going to talk a little bit about that later in the lesson when we take a closer look at Jupiter. But it's the same on Saturn as well. Mostly hydrogen and helium. Uranus and Neptune, also mostly hydrogen and helium, but a little bit less. They have a little bit more of the other compounds like methane and ammonia. So Jupiter and Saturn, 99% hydrogen and helium. Uranus and Neptune, more like 90% or less hydrogen and helium. But we'll take a closer look at all of these planets one at a time. By contrast, the terrestrial planets, including Earth, have meager atmospheres at best. We've learned that the atmosphere of Earth, which is mostly nitrogen and oxygen, with small amounts of carbon dioxide and noble gases, that atmosphere on Earth is like the skin of an apple. It's that thin. Whereas the atmospheres of the Jovian planets are enormous. But let's take a look. On slide 10, there's a really great picture that can give you an idea of the scale of all of these planets, especially when compared to the Sun. Notice a few things here. Notice all of the terrestrial planets, Mercury, Venus, and Earth, Mars, are absolutely tiny compared to Jupiter, Saturn, Uranus, and Neptune. For example, the planet Earth would fit 3 times into that spot on Jupiter. Just that red spot on Jupiter that is a large storm that's been swirling for hundreds of years. Our entire planet would fit 3 times just into that spot. So it would take hundreds of Earths to fill up Jupiter. And when you compare Jupiter to the Sun, my goodness, the Sun is just enormous. So it might be interesting now to go back to slide 6 and take a look at that picture of the Sun, the terrestrial planets, the asteroid belt, and the Jovian planets. And now compare that to slide 10. Now understanding the true difference in size between the Sun, the Jovian planets, and the tiny, tiny terrestrial planets, you can get an understanding that if you were looking at our solar system from the outside, like in this picture, it would never look like this. In this picture on slide 6, Jupiter looks larger than the sun. So if you saw the sun like a tiny yellow dot, Jupiter might be just a speck. And Earth, Mars, and Venus you would not see at all. But let's go back to slide 10 and move on. The formation of the solar system. On slide 11, yeah, great question. So we've got this enormous sun, these 4 tiny terrestrial planets, and then these 4 Jovian planets that are much larger than the terrestrial planets, but still tiny compared to the sun. So why does our solar system look like this? Why do we have planets at all? It's an interesting question. And there are a lot of scientific theories that try to answer this. One very interesting theory is the nebular theory. So let's take a look at that again on slide 11. We see a nebula is a cloud of gas and dust in outer space. According to the nebular theory, the sun and the planets formed from a rotating disk of dust and gases. On slide 12, continuing, planetesimals are small, irregularly shaped bodies formed by colliding matter. Remember in our last lesson we learned about the formation of the moon, and one theory about how the moon formed was that 2 planets collided. Another planet about the size of Mars struck Earth and disintegrated and created a large field of debris, and we learned that term accretion, the way that debris in outer space, if you have an elliptical plane of orbiting debris, that debris will collide and form into larger pieces, almost like a snowball. It's almost like rolling a snowball through a field of snow. And as that sphere becomes larger and heavier, its gravity becomes stronger and it's able to pull even more smaller pieces into itself. So that matter keeps colliding and accreting and becoming larger and larger, and that's how our moon formed. According to nebular theory, the planets all formed the same way. There's a good picture of this on slide 13. We see under this theory, we start out with a solar nebula, this big cloud of gas and dust, again mostly hydrogen and helium, but small amounts of other elements as well. In the next picture, a lot of that hydrogen and helium pulled into the center by gravity and under enormous pressure starts to burn, starts to undergo nuclear fusion and burn and become a sun. We see the sun forms at the center of the protoplanetary disk. As that disk continues to turn, we get the planetesimals, which you can see starting to form. And finally, through accretion, those planetesimals pull more and more of the dust and debris into themselves, and like snowballs, they grow larger and larger and form the planets. On slide 14, we see an interesting chart of the planetary composition. That means what's in the planets according to their, and it's graphed according to their distance from the sun and their melting point. You can see here, here we have the terrestrial planets, Mercury, Venus, Earth, and Mars. I'm not so sure about this graph myself because I can see a mistake on this. We're going to move on to the next slide. So why don't we cut that? Mercury, the innermost planet. Mercury is the innermost and it's the second smallest planet. It's about twice as large as Pluto, but still very small. And it's hardly larger than Earth's moon. Surface features. Mercury has cratered highlands, much like the moon. Again, Mercury is very small. There's no atmosphere, so there's nothing to protect it from meteorites. So Mercury, like the moon, is constantly being impacted and hit by meteorites. And that's why, just like the moon, it's covered in craters. Surface temperature. Mercury has the greatest temperature extremes of any planet. What that means is Mercury has the greatest difference between night and day. Mercury has no atmosphere. So there's nothing to moderate the temperature. So when it's daytime on Mercury and it's receiving sunlight, it's like an oven. But when it's facing away from the sun, when it's nighttime on Mercury, it becomes very cold very quickly. Kind of like the desert. Like deserts here on Earth, which are very hot during the day and very cold at night. On slide 16, we see the surface of Mercury. Next, Venus, the veiled planet. The surface temperature of Venus reaches 475 degrees Celsius. That's the hottest in the solar system. You might be asking, why is Venus hotter than Mercury? And the answer to that is right in that sentence on slide 17. Its atmosphere is 97% carbon dioxide. Now, you may have heard some discussion about greenhouse gases here on Earth. Carbon dioxide is a greenhouse gas because the carbon dioxide molecule absorbs infrared radiation. Many people are concerned about what carbon dioxide in the atmosphere could do here on Earth, making our planet warmer. But to put this in perspective, carbon dioxide on Earth it's less than 1% of our atmosphere. It's closer to 1/100th of 1% of our atmosphere. On the planet Venus, it's 97% of the atmosphere. So this greenhouse gas is almost the whole atmosphere. So the atmosphere on Venus absorbs a lot of solar radiation, making Venus the hottest planet in the solar system. Venus, on slide 18, Venus is similar to Earth in size, density, and location in the solar system. Thus, it has been referred to as Earth's twin. Venus could be called our twin, but it's probably like our evil twin because with that atmosphere that's 97% carbon dioxide, we can see here it's covered in thick clouds that visible light cannot penetrate, which means light from the sun, visible light, the light that we can see, cannot even reach the surface. So in addition to being very, very hot, it's also very, very dark. So Venus would be like our images of hell, very hot and very dark. About 80% of Venus's surface consists of plains covered by volcanic flow. So it's a planet that's very, very hot, very dark, and no oxygen. We cannot breathe on Venus, and constantly covered in lava. So, not a lovely vacation spot, in other words. And there's a picture of Venus on slide 19. Obviously, this picture was not taken with a visible light camera. I believe this was taken with an infrared camera, but I can't be sure. But if we looked at Venus, if we were in a spaceship flying by Venus and we looked at it, it would not look like this. We would only see the swirling clouds of Venus's very thick atmosphere. We would just see the carbon dioxide clouds. Next, we talked a great deal about Earth in our last lesson, so we're going to skip over it, go to our next neighbor, our neighbor on the other side, Mars. The red planet, very different from Venus. Whereas Venus is very, very hot, Mars is very, very cold. So we're pretty lucky here on Earth that we got a planet that's, just right for life. The Martian atmosphere. The Martian atmosphere has only 1% the density of Earth. So the atmosphere is very thin compared to ours. Whereas Venus has a very thick atmosphere of carbon dioxide, Mars has a very cold, very thin atmosphere, almost no air at all. Although the atmosphere of Mars is very thin, extensive dust storms occur and may cause the color changes observed from Earth. Next, surface features. Most Martian surface features are old by Earth standards. The highly cratered southern hemisphere is probably 3.5 billion to 4.5 billion years old. Now remember, here on Earth, most of our surface features, like our oceans and our mountain ranges, are only a couple 100 million years old at the most. Maybe 10, 50 to 100 million years old at the very most. On Mars, you have mountains and valleys and craters that are 3.5 to 4 billion years. So by comparison, compared to Mars, the Earth is always changing. Mars has stayed the same for a long, long time. 4.5 billion years. That's as old as the Earth itself. On slide 21, we see a really great picture of Mars. Two big spots here on the left side that are volcanoes. Mars, in addition to having older features, it also has more extreme features. For example, the highest mountain on Mars, Olympus Mons, is much taller than the tallest mountain on Earth, Mount Everest. I believe Olympus Mons is something like 3 times the size of Mount Everest. So even though Mars is a smaller planet, half the size, it has much larger mountains and volcanoes. Also, you can see in about the center, going across the middle of that planet, we see what's called the Valles Marineris, which is a very deep valley. And that valley is actually deeper than the deepest point on Earth, which is the Mariana Trench in the Pacific Ocean, where James Cameron just went a couple days ago. So Mars, even though Mars is smaller than Earth, it has higher mountains than Earth and deeper valleys than Earth. And these mountains and valleys are much older than any mountains or valleys on Earth. Water on Mars. Some areas of Mars exhibit drainage patterns similar to those created by streams on Earth. This is a relatively recent discovery, and it's a very interesting one. Images from the Mars Global Surveyor indicate that groundwater has recently migrated to the surface. There's a good picture of that. Slide 23, some rocky features that we think were made by water. Of course, Mars is much, much colder than Earth. So in order for there to be liquid water, it would have to be very, very salty. So scientists think that this liquid water that might exist on Mars, it would be almost like syrup. It would be very thick with salt to prevent it from freezing. So let's move on. From Mars, we move on to our outer planets, our Jovian planets. The first one, Jupiter. Slide 24, we start there, Jupiter, a giant among planets. Jupiter has a mass, and I think this is amazing, 2.5 times greater than the mass of all the other planets and moons combined. That means that if you took all of the other planets, Mercury, Venus, Earth, Mars, Saturn, Uranus, Neptune, Pluto, put them all together, there's still not even half the mass of Jupiter. So maybe Jupiter is a good name. Jupiter is the king of the planets. The structure of Jupiter. Jupiter's hydrogen-helium atmosphere also contains small amounts of methane, ammonia, water, and sulfur compounds. But as I mentioned earlier in the lesson, it's all of that, the methane, the ammonia, the water, the sulfur, and some scientists believe phosphorus as well, but all of that is about 1%. 99% of Jupiter is hydrogen and helium. And of that 99%, most of it's hydrogen. It's like you're looking at about 89% hydrogen, 10% helium, 1% everything else. On slide 25, we see a picture of Jupiter, and here we're looking at one of Jupiter's most distinctive features. When we think about Jupiter, we think of that red spot, that big red storm that's been swirling for, I think it's about 300 or 400 years. We also think of these big bands of dark brown and light brown and white that kind of swirl around back and forth on Jupiter. These bands, it's interesting to point out, they are not different chemically. They're not made of different compounds. It's a temperature difference. And here, scientists are still studying these bands. We're not 100% sure, but what we think is that in addition to the hydrogen and the helium, this atmosphere of Jupiter contains these other compounds like methane, ammonia, ice, also sulfur and phosphorus compounds. And these bands of gas, they rise up to the top. You can see an illustration on the right side of that picture. The gases rise up to the top, and that's that blue zone. And then when the gas has been there for a long time, it's exposed to sunlight, especially infrared light from the sun. And scientists think that it's that infrared light that turns the sulfur and phosphorus compounds brown. So you're not looking at different compounds or different compositions. The white bands are almost like fresh gases from deep in the planet. And when they've been there at the surface for a while, that's when they turn brown. So there's always these convection currents going on within Jupiter, carrying gas up to the surface and then collapsing back down, up to the surface and then falling back down. It comes up to the surface, that light color, the whitish color, and then stays on the surface for a while, turns brown, almost like it's being cooked. Not quite the same as caramelization, but you can think of it that way. It's like the phosphorus and sulfur compounds are being cooked by the sun and turning brown, and then they cool and go back deeper into the planet. Okay, let's move on. More about Jupiter on the next slide. Jupiter's satellite system, including 28 moons discovered so far, resembles a miniature solar system. Jupiter has actually over 28 moons now. They're always discovering a new moon going around Jupiter, but many, many moons. Jupiter's ring system, obviously it's not as spectacular as Saturn's, but Jupiter does have a small ring system. And it's so small, in fact, we didn't even discover it from Earth-based telescopes. We discovered it with a satellite. It was one of the most unexpected discoveries made by Voyager 1. Yeah, so we had to send a space probe out to Jupiter to find that ring system. We can't even see them from Earth. On the next slide, we've got a picture of 4 of Jupiter's largest moons going from left to right: Io, Europa, Ganymede, and Callisto. Notice all of these moons, they look kind of like Mercury, or kind of like our own moon. They're covered with impact craters from meteorites, because they don't have any atmosphere, like Mercury or the moon. So, moving on. Slide 28, we're going to take a look at Saturn. Saturn, the elegant planet. Elegant, the beautiful planet. The most prominent feature of Saturn is its system of rings. That's what everyone knows Saturn for. It's the ringed planet. Features of Saturn. Saturn's atmosphere is very active, with winds roaring up to 1,500 kilometers an hour. That is faster than the fastest hurricanes here on Earth. That's faster than the fastest tornadoes on Earth. So you've got giant storms whirling around on Saturn that are stronger than any tornado on Earth. Large cyclonic storms similar to the Great Red Spot occur in Saturn's atmosphere. So Saturn, if you look at that picture on slide 29, that's a computer-generated picture, obviously. But the surface of Saturn, it looks much calmer than Jupiter. If we go back to slide 25, we look at Jupiter, we see those bands, those belts of light and dark gases. We see that big red spot. It looks very violent. It looks very stormy. When we go back and look at Saturn, Saturn, by comparison, looks very calm. But that's actually deceiving, because in reality, Saturn is very stormy. There are a lot of little cyclones on Saturn that we just can't see. And its surface is very violent, very, very windy. Saturn's rings. Yeah, again, what Saturn is most famous for. Until the discovery that Jupiter, Uranus, and Neptune have ring systems, this phenomenon was thought to be unique to Saturn. Most rings fall into one of 2 categories based on particle density, okay? Saturn's satellite system consists of 31 moons, and again, like Jupiter, this number will be different next year. because we are always discovering new moons around Saturn and Jupiter. Titan is the largest moon, and it is bigger than Mercury. Another interesting thing about Titan, it is the only moon in the solar system that has an atmosphere. So Titan is more like a little planet moving around another planet because it's larger than Pluto, it's larger than Mercury, and it's large enough to have an atmosphere. That's why some people have wondered if maybe if there was life outside of Earth in our solar system, a good place to look would be Titan. Obviously it's very cold, but it's a rocky world with an atmosphere. So there's a possibility that there could be some form of life on the moon. Saturn's rings, you can see a good illustration of the ring system on slide 31. Notice those rings, they look like, it looks like an old vinyl record with the different grooves in between the songs. Remember we talked about the way the planets formed through accretion? Those grooves probably formed the same way, with one piece of debris, one piece of rock and ice becoming large enough that it had strong gravity and was able to pull other pieces, all the other small pieces, into itself. And so moving around, it cleared out a path, again, like rolling a snowball through a field of snow. It cleared out all the small pieces, pulled them into itself, and cleared out those little paths that we see in between the bands of A, B, and C. Uranus, the sideways planet, slide 32. Instead of being generally perpendicular to the plane of its orbit like the other planets, Uranus's axis of rotation lies nearly parallel with the plane of its orbit. Remember, I mentioned this at the very beginning of the presentation when we talked about the chart on slide 8. We looked at the length of the year, the period of revolution for Uranus, and we saw that Uranus takes 84 years to go around the sun, 84 years to make that trip around the sun. But I told you that because Uranus's axis of rotation lies almost in the plane of the ecliptic, one side of Uranus will face the sun for about 42 years, and then it will turn away, and it will be away for almost 42 years. So you've got, or really you could think of it like night, or you could divide it into 4. Like you could say morning for 21 years, day for 21 years, evening for 21 years, night for 21 years. Might be a better way of putting it. Picture of Uranus. Next, slide 34, we're talking about Neptune, the windy planet. Just like Saturn, Neptune is very windy, has winds exceeding 1,000 kilometers per hour. Amazingly strong winds, making it one of the windiest places in the solar system. There's a great picture of Neptune on slide 35, and notice that Neptune has this spot, kind of like the giant red spot on Jupiter. Here we've got the giant blue spot on Neptune. Pluto, planet X. Pluto's orbit is highly eccentric. Remember, what that means is tilted. Remember, we saw that in our picture of the solar system back on slide 6. We saw how all of the other orbits, all of the other planets are on this same plane. You've got Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and then Pluto is kind of tilted like this. It's also it's also more elliptical, which means that sometimes it moves inside of Neptune's orbit, where it resided from 1979 through February of 1999. So from 1979 to 1999, Neptune was actually farther from the Sun than Pluto, even though Pluto is considered the 9th planet from the Sun. Mike says Pluto is not a planet. There's some debate on the matter. We've talked about that already. All right, let's move on. So that does it for the planets. Let's talk about some of the other stuff that's in the solar system. The planets, we share this solar system with a lot of other things. The asteroids, they're like microplanets, like tiny, tiny little planets. They are small, rocky. Their diameter can be a few hundred kilometers to less than a kilometer. So I say small and rocky, but that's only small compared to Earth. We're not talking about rock, this big. We're talking about a piece of rock maybe the size of Bangkok. So that's what these asteroids are. Giant chunks of rock the size of Bangkok, revolving around the sun. Most of the asteroids lie between the orbits of Mars and Jupiter. Remember back on slide 6, in that picture of the solar system, we saw that area as the brown area called the asteroid belt. They have orbital periods between 3 to 6 years. Remember, Mars has a period of about 2 Earth years. Jupiter's is about 12 Earth years. These asteroids between Mars and Jupiter have a period of 3 to 6 years. Some of the asteroids have very irregular orbits, and there's a good picture of that on slide 38. You can see this picture shows the Sun at the very center. We see the Earth for some comparison, then the orbits of Mars and Jupiter. Notice the asteroids, these big pieces of rock the size of Bangkok, are all orbiting in between Mars and Jupiter. And then we see a lot of blue ellipses, which are the irregular asteroids. So some of them are floating around in irregular orbits. And notice that because they're so irregular, many of these asteroids do cross the orbits of Mars, Earth, and Jupiter. Some of them do cross our orbits. And some of them do pass very close to Earth occasionally. Next, comets. On slide 39, comets are small bodies made of rock and metallic pieces held together by frozen gas. So frozen gases like carbon dioxide, what we would call dry ice. Comets generally revolve around the sun in elongated orbits. Comets, the main part of the comet is the comma. Now think about what the comma is in English writing. A comma is like this, the little thing we put here to break up a sentence. Well, a comma kind of looks like that. That's why we call it a comma. It's the gaseous component of a comet's head. We've got a small growing nucleus with a diameter of only a few kilometers. It can be detected within a comma. As the comets approach the sun, some develop a tail that extends for millions of kilometers. The interesting thing about the tail is that it always points away from the sun. You can see a picture of that on slide 41. We've got a good picture there of a comma going in its elliptical orbit around the sun. Notice up here at the very top, in the upper right, we see the comma with its nucleus at the center, and then this tail coming out behind the comma made of gases, and dust. Remember that picture back on slide 6? We saw the Kuiper belt. Like the asteroids in the inner solar system, most Kuiper belt comets move in nearly circular orbits that lie roughly in the same plane as the planet. So yeah, it's kind of interesting. You've got the terrestrial planet, then an asteroid belt, then the Jovian planet, and then a comet belt. So kind of interesting organization there to the solar system. Then outside of the Kuiper belt, we have what's called the Oort cloud. These are comets with very long orbital periods that are distributed in all directions from the sun. They form this spherical shell around the solar system called the Oort cloud. The most famous short period comet is Halley's. Its orbital period is 76 years. Yeah, so Halley's appears in the sky every 76 years. Other things to look at in our solar system, meteoroids. They're small particles that travel through space. When they enter our atmosphere, they light up. We call them a shooting star, but the proper term is meteor. And a meteorite is any portion that reaches the surface. Most of them do not. Most of them burn up in the atmosphere. So remember, outer space, they're meteoroids. They enter our atmosphere and they burn up. They're called meteors. But if they're large enough to reach the surface of the Earth, we call them meteorites. But again, very few meteors become meteorites. Next slide, 45. Most meteoroids originate from any one of the following three sources. Number 1, interplanetary debris that was not swept up by the planets, debris that was not accreted. 2, material from the asteroid belt. Or 3, the solid remains of comets that once traveled near Earth's orbit. Remember, yeah, we looked at comets. We saw that tail. Sometimes comets will leave a tail of dust and debris behind them. All right, yeah, here are some major meteor showers. These are meteor showers that occur pretty regularly. And all of these meteor showers, these are times when the Earth, moving around in our orbit around the sun, we move into the debris left by a comet. Probably the most famous is the Perseid shower. That occurs every August, usually in the middle of August, and that was left by a comet in 1862. So about 150 years ago, and still there's enough debris out there that we get a cool meteor shower every year. Yeah, the Perseids are probably the most famous. But you've got a cool list there of all the other meteor showers that occur every year. And again, they occur at the same time every year because that's when Earth is moving into that debris field. It's just sort of sitting out there in the path of our orbit. Alrighty then. With that, we'll go ahead and conclude our lesson. We'll conclude our tour of the solar system. Hopefully this lesson has given you a better understanding of the different planets as well as the other objects out there in our solar system. Thank you very much for tuning in, and I will see you next time. Okay. I'm going to go grab a bite. I'm going to come. You going to come with me? Yeah. Dog?